that is partial derivative with respect to delta, and later on we will use the partial derivative with respect to the transient internal voltage, and we can sort of, without going into the discussion on damper windings, because that is more complicated, at least for me. I would use a long time to do that. But we could say that in damping coefficient due to the damper windings is sort of the partial derivative of the electric power with respect to omega of the things that influence the electric power from the subtransient part. But it's, for now, it's just a constant. Just that this constant is rather complex in the sense that depends on several things. It doesn't only depend on speed, of course. You could also make it depend on a rotor angle, and it depends, for example, on the reactance of the grid. So if you have a low reactance and a low angle, you will have a higher angle and a high reactance, for example. But in a certain operating range, you could assume this to be that means that when you put all this together, you simple second equation. So we forget about the transient internal voltage for the time being, meaning that for our analysis we have if we put it up like in a matrix system, we would have and yeah. So we would have 2p50 here, and we would have for delta we would have Ke divided by 2h. We would have if you only look at the damping here. No, it's okay. I want this. Yeah. Because minus. And then, of course, this is driven by something that now is just the mechanical power, or 1 over 2h then, and the mechanical power, so driving force. but we are sort of in position to do very simple analysis. And of course, what we need to take a look at is the validity of this now, taking into account that the power versus angle characteristic is basically sinusoidal form. We need to be sure, of course, that we are in a situation where we have a stable equilibrium. So basically, the synchronizing power coefficient, the K in my functions, that has to be positive. So we are on this slope, and the KE actually just is the slope of that curve. And we must be, our operation must be in this area, otherwise it's not valid, as you say, because the synchronizing coefficient is highest at low angles and increases to 0, becomes 0 at the point here. So that says something about the operating point. And we will also see very quickly that it's not an option to be on this side. That will be an unstable equilibrium. And any sort of motion then, any disturbance will make the power and the angle oscillate around this equilibrium, right? So if we somehow disturb the system so that it has an electric power up here to start with, it will oscillate like this, and the angle will oscillate like that. That is out of the simulations. You could, of course, from the compute you say that this is the A matrix, and we can compute the eigenvalues from determinant as you know, and you get the characteristic equation for that, which is this is the characteristic equation. And note that I try systematically to use my 2h means that it will not be like this, because my determinant is that is where the confusion always starts. Because if I take the determinant, it is lambda times lambda plus d 2h minus, so it's plus 2h no, don't run too fast here. It's the product here, so it's KE times P times 50 divided by H. Now I cancel the 2. It's the same as this one, but that one is a little bit, to me it's not clear if this is per unit or not. But with the characteristic equation like this, it's definitely in per unit. And it's the inertia constant that you're used to in seconds. That is why I put it on this form. And not how it is in the books by Makovsky. But normally the M can be considered as the H divided by omega n, I think, but I'm not sure. So I do it the way I know becomes correct. Oh. And then we can analyze the eigenvalues we get. So usually we would get to complex, two complex, a pair of complex conjugate eigenvalues out of this. And of course we can I should not show this one. The complex frequency of oscillation, of course, is omega divided by 2p, and the damping that we have what is minus sigma divided by absolute value of the eigenvalues, a relative damping of the signal. Of course, you know this well as me, that if you have negative real parts, you have a damped oscillatory system. If you have a positive real part, it's undamped, unstable. Of course, it's real, then the issue is that the real part is, as you know. And you might get some different results depending on the operating situations, and that is something that we can do some analysis on. So when you have access to MATLAB and of course we can I can give you a very simple script I usually make for this, and try to show you. I have now this is impossible for you to see. Okay, but I will distribute it. What it does is I define the up point in terms of power and reactive power that's supplied to the grid. Infinite bus voltage, and I define the necessary parameters like xd, xq, xd dash, xq double dash, xd double dash, if I want to include the formula for the damper windings. And I establish the power versus angle characteristic. And I establish the matrix and do the computations. And then if I run this script, what I did now is I just said that power is 0.8 per unit, 80%. Q is not defined, is it? Q equals, let's say, start with 0.2 then. Then I could strange. Yes. And infinite bus voltage is 1.0. And then try to run. The other parameters are, for example, my inertia constant is 3.1 seconds. And when I run this, what I print, and this is for you to show, as you can see. This is the power versus angle characteristics, and this shows the difference in a way. This is the steady state based on the steady state parameters, and this is based on the transient parameters. But what you should note is that at 0.8, at the operating point, it's the same, of course. And I can zoom in to show that better. Like this, maybe. Because here you see the actual operating point better. That is, so the synchronization constant is the slope of that curve. So that is when after a disturbance it will oscillate against this, but it will somehow end up in this point, right? So that is, it's easy to confuse out as having two different curves, but it's, then you have one have to remember that these are sort of steady state characteristics, and they don't say anything about the dynamic as such. But that can be. But what we get then is what I did do then was to compute some eigenvalues on that. These are shown here, but it's not easy to see, perhaps. It's actually with a damping of 0, so it gets 0, of course. Which we have. And we can go back. So in any case, we get oscillatory frequency of 1.4 hertz and a damping of something around 4.5%. That is what is, if you can see the numbers here. But it's not important. It's important is that it's easy to compute. And I could also show you for this model in if you implement this in Link, we talked about with the swing equation here and the integrator for the angle, which are sort of displayed in a plot. We can do exactly the same. And then we can look at the parameters. Grid voltage 0.8. Damping coefficient is 5. Inertia 3.1. Then it should. Then we can simulate that. And what we do now is that I essentially simulate the short circuit here for and which is cleared after 0.2 seconds, I think. That's what I set. Full clearing time 0.25, okay. Or we should actually to demonstrate now the small signal behavior, we should have a shorter time, clearing time. Then we can have a look at what happens. You see the oscillations along the power versus angle curve. And here's the angle, the acceleration, and the speed. The point is that you have the oscillations sort of happening along the power versus angle curve, which is fairly linear in this range. So it's sort of more or less valid to assume that this is a linear system, so we could apply the linear theory, and you get a damped oscillation, and you see the frequency of oscillation here, probably around 1.5 hertz, as if we count the number of oscillations. 1, 2, 3 in 2 seconds, so 1.5 hertz. So you see that there's a fit between that and the result we got from just computing the eigenvalues. But what we need to look at then is what happens if the fault is more severe, if we put it like 25 seconds maybe. We can rerun for a more severe fault. And then we see another type of curve here. So we see now that the oscillations go on a longer way. And here you see some characteristic differences, right? Is this, first of all, what you see here is that it's something strange here, right, in the start. Power has a dip here. It's because it oscillates above the top here, and it comes down again, get down and up again, and then goes up here and down. So clearly, in this case, it doesn't make sense to so we need some other tools for the analysis of large disturbances. That's the main point here. And we can play with that, but we can make that sort of an assignment for tomorrow to play more with this one, so to see the differences. But you will have different behavior depending on the operating point, depending on the disturbance. But from the linear analysis, you only get a snapshot of the small disturbances. What would happen with small disturbances? So, summary of this. Is that when we look at large disturbances, which we often refer to as transient stability, we have the same starting point, we have the same. The difference is that linear analysis is not sufficient, so we need to stick to the nonlinear models. And when things are nonlinear, we also have to define our disturbance, because whether the system is stable or not depends as much on the disturbance as the system itself, right? So when it comes to analysis of large disturbances, that many handy mathematical tools, so we have to, usually we do simulations. We trial and error, simulate a certain fault, and we look at the simulation result and see if it's stable or not. There are some other, we could use some techniques based on the Lyapunov theory, or we could, for simple, do a simple assessment, we would use the equal area criterion, which you probably have seen. When you use the equal area criterion, you do some simplification again. For example, that you neglect the damping. Maybe that's not so critical because during the first swing, the damping is not that important maybe. And you must essentially assume that the magnetization of the machine, the internal voltage, remain constant. If you do that, one can make an assessment, but you need to stick to the nonlinear model. And you often do the classical modeling, so instead of having separate dq and xq, we only sort of refer to the transient d-axis reactance. It should be the transient here. I maybe haven't. And if you do that, and you simple, and the internal voltage, transient voltage is constant,